I'm glad it went slow. I mean, I still worked in the daytime, but it was definitely nice to have a little bit of a break there. Hoping this is going. No, that's not what I want.
This is the
yeah, quiet. Why is this not showing up? All right, we're just gonna make sure something here. Whoa.
Yeah, seriously. Like 3 nights of sleep.
All right, cool. We're in business. All right, welcome back. It is 5 minutes past 4, so we are gonna get started. Dun, 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 dun. I feel like we've been away for so long. Everything's rusty, right? Just circle stuff. All right. So welcome back from spring break. We begin our trig either review, probably a review for most of us, but I did ask a couple times who's not had any experience with trig, so maybe the first time you've seen it. Yeah. My goals tonight, really introduce, if you've never seen it before, radian measure. I think most of us have. Give a little backstory here about kind of really what it is, because I could just tell you right now its definition. We could practice problems, and that's probably what most of us want. And then just buy a textbook and read a textbook. But you're here to enhance your learning, to understand, to think more critically, have a better background. So we'll build up what a radian truly is. We will compare that to degree measure of angles. We'll talk about angles in general, how we can imagine them geometrically as a picture. I think most of us hear angle and we immediately think triangle, but we'll go from there. We'll talk about something called a unit circle and some interesting functions, actually 6 functions, typically called trig functions, but I like to call them, why is that? Oh, this is showing me your screen. You need to you can't be using that.
Oh, is that me?
Yep.
Oh, sorry.
Yeah, so I didn't think that would affect it, but that's obviously what was going on there. So.
Oh, I'm okay.
Let's see what else there was. So unit circle, and then 6 interesting functions, typically called the trig functions. Yes, they're called trig functions, but I like to think of them as circular functions because they're going to be based off a circle. What else we're going to do tonight? Look at some special angles. We have a busy night. You guys ready? Homework, bottom line up front. So I'll say the majority, so that's 50% plus some, completed the rational functions that we started the lesson after the test. So I guess not this past Thursday, but a week ago from Thursday. So that is closing for full credit this Thursday. Then it enters its late credit phase, so 2% off per day for 7 days, not even 7 days, 5 days. So that closes out for late credit this weekend. So if you're looking for full credit, you have tonight and tomorrow night to get that done. Homework on everything that I just mentioned in terms of trigonometry. As usual, we'll be doing 1 week from today for full credit, and then enters the 5-day late credit period. So there is quite a bit of homework. I'm not going to lie. If you put it all off, if you took a vacation, cool, then you're back at it now. I will say there's at least one student who's already got all of this done. So it's attainable. Everything's done so far. And a few of us already kind of chipped away at this because I posted it last night. So if you have background in this, it's not that impossible. All right, here we go. Welcome to trigonometry, aka circular things. Okay. So I'm going to introduce us into radian measure. On Earth, a circle has 360 degrees. And yeah, I'm being serious. On Earth. We never say on Earth. We don't say on Earth 1 + 1 is 2. Because on Mars, 1 and 1 is 2. That's going to make this is 2 on Mars. This is 2 on Jupiter. 1 and 1 is 2 on Jupiter. 1 and 1 is 2 everywhere in the universe. But only here on Earth is a circle 360 degrees. I'm serious. So why? Why only here on Earth? And if you knew this, I'd be pretty impressed. So this is just a little potpourri, a little getting us going. Why does a circle have 360 degrees? Turns out it doesn't, except here on Earth.
Maybe because it's relative to the planet, like the shape of the planet.
I mean, I've been stressing the word Earth. So 360 circles Earth. Yeah, go for it. You're probably right.
I was going to say it's very similar to how many days we have in a year.
Exactly, right? So we have our big ball of fire called the sun. And we have our planet, not the first one, not the second, our planet Earth right there. And our ancient ancestors wanted to survive, so they studied the stars and patterns and figured out, this idea of going around the sun, studying the stars, picking our crops, getting our winter jackets out, knowing when to get in the car and drive to the beach, because that's what they did back in the 800 BCs. Got in the car and went down to Narragansett. No, all kidding aside, they didn't know like this behavior, this idea of a circle, repeats itself every 365 days. And that's why a circle on Earth has 365 degrees.
Why is it 365 degrees?
Oh yeah, it's 360 degrees, not 365. So why the heck is it 360, not 365? You fell into my trap. This is working as planned. What's up?
It's because the rotation of Earth around the sun isn't like a perfect circle.
Okay. Maybe. I wasn't there to ask the ancestors why they went with 360 versus 365. Any other ideas?
We use the degree measure for measuring a circle because it's a unit from minutes and seconds, which was bisections of a sundial measured off of a 12-unit system.
Oh, okay. So there's a lot of history here, and it sounds like, maybe even a little more than me. So maybe it has to do with the sundial, which was built off of 12 parts. Very well, potentially. No one knows. Why not 365? But we have hypothesis. We can guess. I like to believe that, with all this studying, and if there's ancient scientists and mathematicians who are studying this for a reason, who are probably going to build something or do something amazing with it, and they have, we're still here. They're probably going to divide this by 2, where 365 divided by 2. I mean, if they figured out that the Earth goes around the sun in a circular-ish behavior in 365 days, they definitely were probably familiar with decimals, but they were also smart enough to be like, we're going to be dividing by 2, and let's try to avoid decimals. And yeah, so that's my hypothesis. I just think because you can divide by 2, you can divide this by 3, where 365, you can divide by 3, but more decimals. You can divide this by 4, 365, you can divide by 4, but more decimals. All right, so at least my opinion on why why on Earth a circle has 360 degrees. Interesting. But a more universal way to measure an angle, regardless if I'm on Earth or Mars or a planet far, far away in a deep galaxy called the Death Star. I don't know. You could be anywhere in the universe. And I'll still have my 2 feet, unless the aliens ate them, but I'll still have my feet, and I'll be able to count, not knowing what planet you put me on or anything about how it rotates around its sun. I could definitely count some steps from a center, like 4, 1, 2, 3, 4. I'm using 4 just because it's a nice number. And from that center, maybe I like anchor something down with a rope. Again, I don't need to know anything about rotation around the sun. And I can walk in a circle perfectly 4 steps away from the circle. So I could, from the center, sorry. Right. So here's me anchoring something, and now I'm going to walk around. Well, if this was 4 steps, that's called our radius. And here's what's interesting. And I know some of us are writing some of that stuff down, so I'm not trying to go too quick, but if these are my 4 steps, and I walk what we call along the arc of exactly the same number of steps. Ready? So I'm 4 feet from the center, and now I'm going to go 1, 2, 3, 4, stop, turn, and go back to the center. There's an angle called a central angle. What color do I want to use here? I'll go with blue. And we needed a way to name this angle. I'm not from Earth. I don't know about your degree system, as you call it, but I will call this 1 radi. Man, I walk 1 radius. I should call it 1 radius, but we already used the word radius to represent this. So let's call it 1 radian. And that's what a radian measure is. There's your first example of a radian measure. Why stop the fun? I like walking around circles on ancient or distant planets. What if I took 8 steps? Well, I've really gone 1 radius twice. I've literally traveled a length across the arc that is 2 radius. So I will call that angle 2 radians, and so on and so on. If we went, or I went 4 radii, a total of 12 steps, radius, arc length, all this, and this angle in the middle, we will call 3 radians. So what's the relationship between S, R, and theta? What equation can we write that connects this, this, and this in all 3 diagrams?
For one thing, I keep seeing the arc like though for every time. You started with 4.
Yeah, I could. Okay. So I'll give you a new example. You give me a new example. Give me a new radius.
Maybe 3. Let me cut it.
Center, 1, 2, 3. Anchor, rope, walk around. Okay, I got a radius of 3.
Yeah.
I'm only going to go 1.5. Then what's that measure? Half radian. So what is your brain doing? Here's the arc length. Here's a new radius. You still have an angle. What equation relates these 3 things? I don't know. Your brain told me. How did you know 1/2? Let me ask you this. Suppose I say the radian measure is I'll do something like this. Suppose I say this is 2.5 radians. And I'll tell you that this number is, I don't know, 12. Theta, radius. Can we figure out the arc length? What is this then?
What?
4?
Four again?
Why 4? Well, I don't think it's 4 because this is 12 steps. So I did 2.5 of those groups.
The radius times the angle equals the arc.
There's a claim. Radius 4 times 1 equals the arc. 4. That actually makes sense to me. This is the radius. This is telling you how many radiuses you walked. So if you did a radius once, the arc length is 4. This is the radius. This is telling you how many you walked. So if the radius is 4 and you walk 2 radius, you must have done 8. If the radius is 4, the radian is 3. You did 3 groups of 4. 4, 4, 12. If the radius is 3 and you only did 1.5 of these, let me rephrase that. You didn't do 1.5. You did not even a full one. You did half a one. Okay, yeah. So 3 times a half would be 1.5. And therefore, 12 times 2.5, we would have done 12 steps, 24 steps, and half of 12 is 6, 30 steps. Beautiful claim. Radius times theta equals arc length. That's what radians is. I'm going to come to that in just a second. But I want to talk about this radian. So what can I do to both sides of the equation to isolate the angle?
Divide by R.
Divide by r. And this is the definition you'll find on Wikipedia, in a textbook, anywhere you want. You just came up with alien math. You just figured out a way to measure an angle, whether you're here on Earth or the Death Star. You count your radius. Oops, I got this wrong. I got this wrong. That would have been too bad. S over R. My bad on that. Where this is your arc length. And R is your radius. And this is an angle, not in degrees, but what we call radians. Okay. It's in a big bolded box, so I guess that would be important to know and memorize. Radian measure is considered unitless because I was talking about my arc length being steps or feet. The radius was steps or feet. So if you think about the actual labels, feet over feet would end up canceling out. And therefore, a radian is a unitless measure, according to Wikipedia. But I don't need Wikipedia to tell me that. I proved it. Whatever you measured in is going to cancel out. And that's why, what's an important note there, we don't put a degree symbol on radians. Why the heck would you do that? There's 2 different things. So don't put degree symbols on radians. Don't put any symbol on radian. And that's also important, that if you put something on a test and you meant 30 degrees, but you put 30, you're not going to get full credit because I'm going to think you meant 30 radians. 30 degrees and 30 radians are not the same thing, or are they? We'll find out. Radians are unitless. So let's apply it. What would the central angle in radians be if the arc length was 56 and the radius is 7? You can do this conceptually, or you can do this with the formula. Theta equals S over R So if we substitute it in, 56 and divided by 7, 8. Take your arc length, radius, and that's going to be your measure. Okay. Can we find arc length if we have these two pieces of information? Yeah, we can actually use what was claimed in class. S equals R theta. So if you like studying two formulas that are actually the same, go for it. I like studying one formula. Theta is S over R. So me personally, since this is my tablet and my notes, I'm going to write this. I'm going to substitute in the 2.5. I'll substitute in S with S, and that for 8. And then I can say, all right, if I want to find this arc length, just multiply both sides by 8, and we would get 20 as our value. Find a radius. Given a radian and an arc length, you know where I'm going with this. Maybe you do. S over R. So 14 over 3 equals 14 over R. I'm thinking R is 3. What's the radian measure if our arc length is 28 and R is 1? Well, that's cool. If R is 1, the arc length is equal to the radian measure. If R is 1, every single time, the arc length and the radian measure are going to be the same thing, the same number value. So I'm not even going to waste time. This is going to be 4.25. Here's the big one. You tell me. How come? Yeah. So if we use the formula, I'll do this in color because this is actually going somewhere. This is S 2 pi R. This was the radius from earlier over R. And that is the angle measure in radians. What happens to radius every single time? Cancels out. Meaning, I don't care how big or small this circle is. It could be like a ½ inch radius or 10,000 mile long radius, which would be a massive circle. It doesn't matter. If the arc length is 2 pi R, the angle is 2 pi. Why am I making such a big deal about 2 pi R? What common geometry formula is 2 pi R?
He's not taking a the radius from degrees or something.
So here's a hint. It's an arc length. It's in the arc length column. So arc length is the part of a circle that's, I don't want to use perimeter, but I'm thinking it's a famous knight. I think many people called him Sir. Geometry. Sir. Oh, sir. Yes, that's it. It was a circumference. No, circumference. That's right. It's CIR. Thank you. That's the total distance around a circle. And it doesn't matter how big the circle is. One arc length around a circle is called circumference. we say that's what? 360 degrees, because we are on Earth. So I don't want us to walk away saying, oh, I can't use 360 anymore. No, 360 is one rotation. 360 degrees is our degree measure. And we've now said, in terms of radians, it's 2 pi. The entire arc length of any circle is 2 pi r, called its circumference. Applying this fact to the relationship we just discovered, we can establish that a full rotation measures 2 pi radians. One rotation, 2 pi radians. Then it just makes sense that a half a rotation is how many radians? Pi. Bro. Pi is about what number? Is that half a rotation? No. That was how many radians? 3. What's half a rotation? Right, a little bit more than that. And what did I say a half rotation is? Pi, a little bit more than 3. So if I said, yo, I went this far, if I literally went halfway around, then that would have been that little bit extra right there. Right? That tiny bit more is what makes up the pi. So another big bold box. One rotation is 360 degrees, which we use that as a unit, as a symbol. And we write 2 pi with nothing, and it means radians. And even more importantly, half a rotation is 180 degrees, is pi radians. We might not have learned why in this way. I'm willing to bet you didn't learn why in this way. You might have even came to this course already knowing that fact, but now you literally just did alien math and connected it to Earthling math. 180 degrees on Earth is the same as pi radians in the entire universe. Only here on Earth is a circle 180 degrees. All right, I'll stop saying that. That's my build up to this. Therefore, now we can convert degrees to radians, literally right there. From degree to radian, divide by 180, multiply by pi, or you can just multiply by pi over 180. Think about that. We're starting at degrees, so I want to ditch degrees. So I'm going to put the degree measure in the denominator and switch to the radian measure. Very similarly, to go from radians to degrees, we could divide by pi and then multiply by 180, but I'll just cut to the chase. You're going to multiply by 180 over pi. Literally stems from right here, knowing the conversion rate. If you're a great memorizer, memorize. If you want to become a better thinker, don't memorize. Learn to understand. So I always have to forget that. Like my brain had to literally think what I'm about to do. Here's how I do it. 15 degrees, I'm going to multiply. I'm starting at degrees. All I remember, because this works beyond mathematics, this works in science. You want to convert money, Celsius to Fahrenheit, so temperature, anything you want to convert from one thing to another, what you have, you ditch it. So I'm going to put degrees down below and radians on top. And I know 180 degrees is pi radians. So I have 15 times pi over 180. And typically we just reduce that down. So a lot of 5s, 10s, 3s. Thank you, ancestors, for using 360, not 365, but all right, divide by 5. This would be 3 pi. And let's see, I think 12? Yeah, 3. No, is it? Divide by 3? No. That's not true. That would be, I'm dividing by 5, my bad. 20 and 10 and 3. That doesn't seem right. Why can't I do 180 divided by 5? 20, 10, 30, 36? Ah, there we go. Pi over 12. 15 degrees is pi over 12 radians. Convert 7 pi over 18. Emphasizing no label, no units. It must be radians. 7 pi over 18, 2 degrees. Multiply by, get rid of radians, go to degrees. And I'm going to work smarter, not harder. Pi's definitely going to cancel out my final answer. 18 goes into itself once and into this number 10 times. So instead of making bigger numbers, I'm going to cancel before I actually multiply. And we get a value of 70 degrees. Okay. A little background knowledge on why our planet has, or why our circle has 360 degrees. But more importantly, this was to help us build the most important facts up to that point. The first important fact of the night, know the definition of a radian measure, be able to apply it, led to something interesting. 2 pi r is circumference. So if we apply a full distance around a circle of radius r, second big point is that one rotation is 360 degrees is 2 pi. And while we could use this conversion factor all day and night, this is the gold standard. So basically just smack everything with divide by 2. And half a rotation is 180 degrees is pi. With that, we're able to convert to our universal measurement of radian from Earth. And that's what a radian is. Now we're going to consistently work the rest of the night between radians and degrees. Really stretch our brain. Angles of rotation. A standard position angle, or an angle in standard position, is an angle on the coordinate plane, number one. And we imagine that the initial side is on the positive x-axis. Oh, I should write that in there. Positive x-axis. So it's like we're going to start over here. You're going to bend at the origin. Your vertex is the origin. And if I say rotate, we'll use earthling numbers. 90 degrees, everyone's comfortable with that. But actually, I just made a choice because that's 90 degrees too. But those are two different positions. So I'm like, yo, meet me. You're right here. Rotate 90 degrees and you'll find me. Haha, you found me, actually. Haha, you missed me. So 90, I need a choice. Do I want to say opens upwards or opens downwards? More historical fact here. Choice had to be made with our ancestors. But what were they studying? What goes like this every day? The sun. And that's what they were using this for. They were actually trying to survive. So since that's what they were going to use the most, they decided this way is positive. And that's why our quadrant system goes 1, 2, 3, 4. Mad interesting stuff. Angle of standard position. We start in the positive x-axis, vertex's origin. Positive angle means rotate counterclockwise, and a negative angle means clockwise. And you mentioned sundial. I'll let you put it together why this is called counterclockwise and this is called clockwise. Sundial is the biggest hint there. In either case, no matter how you rotate, you eventually stop at 90. This is your terminal side. All right. So to give it more visual than just my arm in the air, we're going to sketch angles in standard position. We're going to state the quadrant that they terminate in that I just reminded us go 1, 2, 3, 4. And then we're going to find the measure of the acute angle formed with the terminal side and the x-axis, which is formally called the reference angle. So 135, first we sketch a plane. Here's our initial side along the positive x-axis. Here's my vertex at the origin. We do have some common knowledge because we're in pre-calculus in college that this is 90 degrees and this is 180 degrees. So 135 definitely in over here. Now, oops. Is that a good sketch of 135? Well, I guess it's not drawn over here, here, and there. So define good and define what you mean a sketch. But I think we can do a little better because if this is 90 and that's just a little bit more, I don't know, I wouldn't say that's really 135. Just like that's probably not a good sketch of 135 either. So I'm just going to kind of throw it right there. All right. And that's what I mean a sketch. Use some general estimation. There we go. Initial side, vertex. Because it's positive, I rotated this way. 135. State the measure of the acute angle formed with the terminal side. So here's our terminal side. Here's the x-axis. So there's actually two angles formed. Again, x-axis, terminal side. Here's an angle, and that's a different angle. Which one is acute? What does acute mean again? So adorable. What's acute mean?
Yeah, it's smaller one.
Smaller than what number?
Smaller than 180.
It is smaller than 180, but 135 is not acute. It's also smaller than 90. So it's bigger than 0 and smaller than 90. That's important later. It has to be positive. Acute angles have to be positive. So it has to be a number between 0 and 90. That number is bigger than 90, so that's not the acute angle. We want this angle right here, called the reference angle. So what does it measure? 180 minus. All right, so a few other things going on here. Here's 135. That would complete the rotation. So all of it's 180. Subtract the 135. 45 is degrees, because I said to take off a point if there's no labels. Now 45 radians, 45 degrees is our reference angle. And that's what our reference angle is. Yep. Onwards we go. Nothing else to do there.
So if the reference angle in the third quadrant, would we take the smaller
acute angle, always the smaller angle
Okay.
with the x-axis. Negative 300. Standard position, always start here. Negative means we're going to rotate clockwise. That's 90 clockwise. That's 180 clockwise. That's 270 clockwise. So 270 and 30 more would be that. Cool. State the quadrant it terminates in. 1. Let me go back to the last question. This is quadrant 2. This is quadrant 1. And I'll do this as many times as we need to see it. This is the x-axis right there. This is our terminal side right there. So there's this angle, magenta to red. That's clearly bigger than 90. And then there's magenta to red. So this is the angle we want. That's our reference angle, which always is a positive number between 0 and 90. So how did we figure out what that was?
We can do 90 minus the 30.
Oh, okay, yeah. So we figured out that this was 90 clockwise, 180 clockwise, 270 clockwise. We knew we had to go 30 more clockwise. So 30, and that's going to be 60. $60 is our reference angle. 400 degrees. Start here. Rotate upwards, counterclockwise, 90, 180, 270, 360, and 40 more. We've done more than a rotation. There's the angle. That's what 400 degrees would look like.
Since we went 60 more.
Since we went 60 more, 40 more sounds better than 60 more, but you got me saying that. Yeah, 40 more. So not to overkill this, 90, 180, 270, 360, and we just had to go 40 more from the 360. 40 is your reference angle.
So in a sense, we're taking the given number there, the 400, subtract the rotation, entire rotation 360.
Did that work here though? It worked right there. If I subtract 360, it's definitely not going to bring me to 45.
No, it's not cool.
And I could continue to break that argument, but I like that you're thinking about it. If it's more than a rotation and terminates in quadrant 1, that's a lot of stipulations. But if it's more than one rotation, can it be more than 2 rotations though? More than 1 rotation and ends in quadrant 1, subtract 360, yeah, that would find it. If you're trying to generalize, we're going to get to that. Right now, I just want to make sure we absolutely can completely conceptualize what's going on. The easy ones. I'm not even doing these. These are so easy. The degrees were actually harder. So, no, these are easy. These are easier. That's quadrant 3. Reference angle is pi over 8. That's not in a quadrant at all. And that's in quadrant 2, pi over 21. Done. That's so much easier in the radians. All right. You guys are good on that, right? Totally get it. No, it really is. Ready? I'm going to take the long road just a couple times, but show you how freaking easy it is. This is 0 radians. Here's the interesting part. How many radians is half a rotation? What's the number in front of pi? Which is the same as blank over blank. Give me an example. Blank over blank. 1 over 1. Give me a new example. 2 over 2. Give me a new example. 8 over 8. Man, why did you think of 8? Eight out of 8. Where's 9 out of 8? A smidge more. If I lost you, this is 4 out of 8, also known as pi over 2. 1 pi. I'll go over here. Yes, no, that a full circle is 1 rotation, is 360 degrees, is 2 pi. But know that 2 is the same as 16 out of 8. 4 out of 8. 8 out of 8. 4 and 4 more and 4 more and 4 more. So that means this is 12 out of 8. Bro, all you have to do is skip count at first, and then it's going to be up here like my brain. I said that this was in quadrant 3 because I was thinking 8 out of 8 brings me right here, and I just need 1 more out of 8. So I knew it was in quadrant 3. And by the way, once I draw this in, that's going to be the smaller angle, right? Because I know it's just a little bit more. This is the bigger angle, so 1 pi over 8 is the reference angle. Radians are easier to work with than degrees once you truly understand it. All right, but I will go take my time. Boom. 1 out of 8, 2 out of 8, 3 out of 8, 4 out of 8, 5, 6, 7, 8 out of 8, 9 out of 8. Boom. It's positive, so there's 9 pi over 8. I don't know how else to say it. If you're at 8, you need 1 more pi out of 8 to make 9 out of 8. Quadrant 3, there's the angle, there's the reference angle. This is not, I wish I didn't put this here, but I did, so I'm going to live with it. There's one thing I don't like about this. I have no problem with negative 3 pi over 2. It's actually a super common angle that we're going to see. Negative means we're going to start on the positive x-axis, rotate clockwise. Now I know this is pi over here, so I can do 2 over 2, which is also the same as 1. And then if this is 1 pi, this would be pi over 2. Or this would be negative 1 pi over 2, right? So if this is 1 pi, which it is, then this would be half of it, pi over 2. But I'm rotating clockwise. So there's negative 1 over 2. There's negative 2 over 2. And here's negative 3 pi over 2. Do you see how I did that? Because positive, like here, earthling math for a minute. 90 degrees, said I had to make a choice up here. So negative 90 degrees is here. 180 is here. Negative 180 is there. So that, cool. But now negative 90, negative 180, negative 270. Yeah, just clockwise. Why don't I like this question? Which quadrant is that in? It's not. It's a divider. Second reason I hate it, it's not even that I made a mistake there. I can't say this word. Quadrantal. I think that's how you say it. It just looks weird. It's spelled weird. But a quadrantal angle is an angle that separates 2 quadrants. So basically, anything that's on the axis. It's not in a quadrant. I'm probably never going to say that word again in this course. Because here's another reason I like it. What's the reference angle? There is no acute angle either. So this was just a bad example. Or maybe it was a good example to say, this is actually a bad example. There's not quadrant and there's no reference angle if you're separating, right? Because an acute angle has to be strictly more than 0 and strictly less than 90. 90 is not acute. 0 is not acute. In between there is acute. So I'll let it go. All right, 20 pi over 21. Here's my go-to if you haven't caught it. And if you're looking for some direction, here it is. Gotta know 180 is pi. The next way to kind of get better at this is know that this is 1 pi, and 1 can be thought of as 2 over 2, 8 over 8, and 21 out of 21. The next thing I would do is know that this is 42 out of 21. Right? So that would be a full rotation. Overkill, but that's helpful. So now start at 0 and go to 20. Well, that means I'm not even going to get all the way around. Not even going to get halfway around. I'm going to be a little bit short. Boom. Again, now this would be a good estimate. How much short am I? What would have got me all the way there? 1 pi over 21. If I had just one more, it would have completed it all the way. That's the reference angle. It can be easier. Bring you to 180 and then just compare the top number. A coterminal angle is an angle that has the same initial side, same initial and terminal sides, but vary by, let me draw a picture, you tell me. Bo already kind of said it. Probably doesn't even know it. If I rotate 30 degrees, I'd be something like that. If I rotated 390 degrees, and by the way, let me be a little more careful. There's 30 degrees. If I rotated 390 degrees, I'd be like there. Same initial side, same terminal side, different rotation, no doubt. By the way, overkill, rotate negative 330 degrees, 3 different rotations, but they all started here, they all ended there. Those are coterminal angles. So I just used 30, 390, and negative 330. Here's another example, 320, 360, and negative 340. How can we build coterminal angles? You simply add how many degrees? Or subtract. So you add or subtract multiples of 360. Makes sense to me, right? Here's another just silly analogy. Here's my dog in the morning, boom, chases a squirrel. As my dog ran this way, ran through my flower bed. I'm all mad. So I train the dog to get the squirrel, which is still right there, but run this way. But what my dog really does is run in circles. So you can just keep adding rotations of 360, depending on direction, subtracting 360. And what is 360 in degrees, in radians? 2 pi. So that's all a coterminal angle is. It's same starting, same ending, and a different rotation in between. How do you build them? You add or subtract. So even though I have it right there, I'll put it nice and clean. In degrees, add or subtract 360s. In radians, add or subtract 2 pi. Okay. I just recently added this into my notes. Least positive and greatest negative. They are weird words, but let's just break it up this way. Positive means positive, bigger than 0. So I want to be positive, but as small as possible. So we call that least positive. Negative means this side of 0. And this one really messes with the student. What's the greatest negative? Well, how do we define greater on a number line? The thing that's closer actually further to the right, right? If these are two numbers, this is the greater one, this is the lesser one. So if I'm on here 0, so this is negative, this is the greater negative. This is the smaller negative. So it's as close to 0 as possible, but still negative. Find the least positive and the greatest coterminal angle for 520. So 520, that's already bigger than 360. Can I get it smaller? Yep. I really don't feel like doing math, but I will. I should say arithmetic. 160. That is going to be the least positive coterminal angle. Least positive. How would I find the greatest negative? Subtract another 360. Minus 360, and you'd get negative 200 degrees. That's your greatest positive. Because we can continue to subtract 360, we can continue to add 360, but this would be the least positive and the greatest negative. Negative 487, add 360, so it's going to be 17, no it's not, 27, negative. I already can see what's going to happen if we add another 360. It's going to bring us over. Let's see, 3 brings me to 30, 30, and then I want 233. Least positive. Right, mad simple. 13 pi over 4. I could definitely do this, but I actually like just doing circular math. 4 out of 4, 12. Not 12, 8. Another 4 would bring me to 12. So I'm like over here again. And then 13 would be right here. So I really just want this angle right there. 13 pi over 4 is right here. Do we agree? Four out of 4, 8 out of 4, 12 out of 4, 13 out of 4. I want to remove this rotation. Here's my answer. The least positive, 4 out of 4 plus 1 more pi over 4. 5 pi over 4 is going to be the least positive. What's the greatest negative? That would be negative 4 out of 4, but it's short one, negative 3 pi out of 4. That's how I do it. That's how I got stronger at this. So least positive is 5 pi out of 4. Greatest negative, negative 3 pi out of 4. Or you can do arithmetic, which I'm just going to delete over here in a second. And, well, we wouldn't want to add 2 pi. That would make it bigger. We'd want to subtract 2 pi, which is 8 pi out of 4. So you'd get your 5 pi out of 4. And then you could take that and subtract another 8 pi out of 4. And you get your negative 3 pi out of 4. And you'd get that. But the picture definitely reinforces the concept, right? This just represents you can do fraction math. I could teach anyone how to do fraction math, have no idea what they're actually doing conceptually. I'll skip negative 27 pi over 6 just for now. And I'm going to end this section with common angles to recognize really quickly. Some of us won't do this. We're in our ways. We accept the grades we get. We think learning is fixed. We don't change anything we've done. And some of us will say, I need to get out of this course and pass. So listen up. This needs to be memorized like your social security number. Or not. Not my decision. My job isn't to make you do something. It's to suggest and offer you the guidance how to be successful. Even if you're failing this class and you got to take it again, you're not going to pass it next time around, and you're definitely not going to pass calculus. I'll tell you that. 0 degrees, 0 radians. 90 degrees is pi over 2. 180 is pi. This is 3 pi over 2. And this is 4 pi over 2, called 2 pi. What's 30 degrees? Pi over 6. How come? Did you convert it? Obviously, it is pi over 6. How did you convert it?
Because 90 degrees is pi over 2. So
True. So why is 30 degrees pi over 6?
if you divide that by 3, that would be pi over 6.
And dividing by 3 is the same as multiplying by 1/3. So multiply this by 1/3. Pi over 6. Or you could say 180 degrees is pi, so you would divide it by 6 to get to 30. You can do whatever the hell you want. You could say 360, you divide it by 12 to get 30. Now, that's not obvious, but you could. Some people have brains like that. This over 12 makes pi over 6. This is the gold standard, though, right? This is like the easy one. And this one's equally as good. 90, multiply by a half. That's how I say it. I know it's divided by 2, but multiply by a half gets me 45. Multiply by a half, pi over 4. 90 multiplied by 2/3, I don't feel like doing. So I'm just going to go to 180 and divide by 3. But that's not memorizing. That's how you build understanding. But you want to say pi over 6, 30 degrees. Pi over 2, 90 degrees. 2 pi, 360 degrees. Yeah.
Why don't we landmark 15 degrees and 75 degrees?
You can. But they're just not common angles. We'll find out why these are common right now. Why are these common angles? 30, 45. These are common angles because they're, I'm going to break my promise. They're quadrantal angles. But there's something interesting about them. I mean, they're quadrantal angles, and they're just nice. So what makes these nice?
They're part of the first quadrant.
They're part of the first quadrant, 100% true.
They represent triangles, common triangles.
And they represent common triangles. Not drawn to scale. Let me draw this a little more carefully to scale. All right. Here's a nice little right angle tool that doesn't draw nice. What the heck? I've never seen that in my life. That's something new I just figured out, but now I'm curious how it did that. How do I do that? Yo, I got to learn how to do that. Okay, more to figure out another day, because now I'm going to be obsessed, so I'm not going to even do that anymore. Let's see. I'll draw it this way. I'm trying to draw this a certain way. The smaller angle right here, so this has to be the smallest side. Okay. 30 degrees, 60 degrees. At least that's a little more drawn to scale. I'm telling a lot of history today, I've been talking a lot about aliens today. What do you want to know, aliens or history? I'm going to tell you about history. I had a 50-50 shot of giving you what you wanted. But the reason these angles are so important is historically, believe it or not, there was no TikTok, there was no internet, there was no phones or TV. There was just our brains. All right, all kidding aside, but they were smart math people. And they knew a lot of things. For instance, they knew something called an equilateral triangle. What's an equilateral triangle? All the sides are equal. Give me a number. 3. Cool. Give me an even number. No, we'll go with 3. I like even better. But we'll go with 3. This is 3. And this is 3. What do we know about equilateral triangles in terms of their angles? They're all the same. They're all 60. So this would be 60. And this right here would be 60. And there is our goodbye. There was. There's our equilateral triangle. Do you see it? 60, 60, 60. 3 sides are all the same. But what would we call this? A line of symmetry. I believe that they're going to completely overlap. That's just human instinct, like our ancestors. So if you don't believe it, convince yourself by doing it. But I truly believe it, even not drawing a scale. This would fold right over there. This would fold right over there. This would line up with that. So therefore, what's this side? 1.5. Why did I say choose even?
Now it's messy math.
If this was 30, what would that be? 15. If it was 200, what would the green side be? So now let's really go somewhere with this. Let's choose even, just because it's nicer, in my opinion. If you don't like my opinion, drop my course. I mean, it's that simple. Just, that's it. Can I find the height of this? Let me phone a friend. Hello, Pythagoras. Oops, just Snapchatted someone's Pythagoras, but that's all right. Pythagoras. What's Pythagoras say? C squared, which is the hypotenuse. So I'm just going to right now call this our question mark. 2x squared, the hypotenuse, is equal to
X squared.
Plus question mark squared.
Yeah.
What's 2x squared?
4x squared.
What would I do to both sides of this equation? What would I do to solve for question mark? So the x comes out, this stays in, and your question mark is x root 3. And that's why they like this triangle. Because no matter what number you chose for x, so if you chose 1, this would be 2, 1, and that height would be root 3. If you chose something like, what the heck did you say? 3 halves, then this would be 3. 3 halves is 1.5, and 3 halves would be 3 root 3 over 2. So they could easily figure out all parts of this triangle. Plus, there's just something elegant about it, right? Equilateral triangles, there is something naturally, aesthetically beautiful. And I'll let that go. Why is 45 such an interesting? What's 45 half of? Like, what shape could we use? What geometric shape that we could fold in half and give us 45? So I took I used an equilateral triangle to fold in half to make a 30. What shape would I fold in half to make a 45? David says a square. My phone, Pythagoras just left a voicemail. You want to know what's up? This is 90 folded in half this way. Those would be 45 degrees. And what do we know about a square? If this is x, that's x. And can we find that diagonal? Pythagoras said, just use me again. X squared plus x squared equals our hypotenuse squared. 2x squared equals our hypotenuse squared. Solve for question mark, x root 2. And that's what makes those special. It's the fact that it's half an equilateral triangle and half a square. You ask, why isn't there a 15 or 75? Actually, there should be. Mad cool. But you could figure out 15 and 75 with nothing else than what we've just done here. Takes a little more creativity, but it's never taught. I don't know why it's not taught, but it should be. Okay, because you don't believe me. If we take a 45 and we take a 60, what's the angle in between there?
Subtract those two from 180.
Yep, so what's the angle in between here? $75. So I'll leave you there. And if you're curious, this is a good, you could say, how do you figure out 75 degrees just based on shapes? So you actually take your 45, 45, 90 triangle over here, your 30, 60, 90 triangle over here, you build another cool looking rectangle that I can't remember off the top of my cuff, plus we're out of time, but I know I could figure it out, but I know it starts right from there. So you could figure out 75 in a cool way. We're going to figure out 75 another day, but not using geometry. All right, this is actually a perfect segue into what we need to finish up tonight. But seriously, these are common angles. These are common angles. If you've taken trig, you already know that. So off we go. If you haven't taken trig, then what the heck is all this stuff about trig? All right. End game for tonight, as Taylor Swift would say. This is a bigger section. If it's been a while and you're really, really rusty on trig, you can definitely get through the angle of rotation and radian homework. I've covered everything there. This one, I'll get you through as much as you can. But just looking at the clock, we have about 20 minutes left. Not going to get through everything that's in the homework. It's titled Unit Circle and the 6 trig functions. So the first thing we're going to do, define what a unit circle is. It has a center 0, 0. That's cool because we've been talking about angles in standard position, whose vertex is 0, 0, so we want things to start to come together. Secondly, it has a radius of 1. Its equation is x squared plus y squared equals 1. Man, I really want to prove that right now, but we will do it when we get to conic section. So just put Pythagoras on hold, and that's my big hint here about how we'll actually come up with that. We could do this, like, this is a fact right now. You trust my fact or not, I will prove that fact later. But it's important to know that, at least to get through some of the things that pop up. The radian measure of the central angle equals the length of the intercepted arc. What? Earlier tonight, we've already established that theta radians is S over R. But what circle is this? Which means the radius is 1. So the angle is equal to the arc length. That's what this says right here. Not the degree measured. 30 degrees is not equal to 30 steps. But remember, this radius if I did a radius of 1 and I took 1 step, that central angle is 1. If the radius was 1 and I took 2 steps, the central angle is 2. If the radius is 1, the central angle and my steps, aka the arc length, are the same. So only on this circle makes it a cool circle. What are the coordinates along this unit circle if t, the central angle in radians, because there's no degree measure, is pi? Threw a lot at you. Negative what?
-1.
How come? You are correct.
If the center is 0, 0, and pi is equal to 180, it would be on the left side. So,
Yeah, so this gets really complicated, but I'm doing it because that's what the textbook uses and potentially my lab. So, but basically this question is like, bro, go on a unit circle. So your radius is 1 and rotate like we were doing before. Rotate pi. So half a rotation, 180 degrees. Here we are. What would the ordered pair be? And it would be -1, 0. How come? Because this is a radius of 1. This is a radius of 1. This is a radius of 1. But we know on the coordinate plane, when you move to the left, that just means -1, 0. So we associate the point -1, 0 with rotating pi radians. What point should, or not should, must we associate with 2 pi? What number? 1, 0 is correct. Again, this is what your brain wants to think about. This is 1, all the way around 1. How much do I need to rotate? Literally all the way around. So that is 1, 0. What about 3 pi? Nope. -1, 0. Let's go back to a few things. Standard position. Where's pi? Right there. That's not 3 pi. Where's 2 pi? Right there. Still not 3 pi. That's 3 pi. 1 pi, 2 pi, odd pi, even pi. Odds are over here. Evens are right there. 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, or -1, -2, -3, -4. That's nice to know. So 3 pi, -1, 0. Vocab word of the night, one of many. 3 pi and 1 pi are coterminal. They start and end in the same position, and they're also odd numbers. Okay, they are odd. 44 pi, spoiler alert, even pi. So 1, 0. Negative pi, odd pi. Negative odd, doesn't matter, it's odd. We're all over there. This would just be a crazy amount of rotate. It would be literally 9,037 half rotations. I know it's a weird way of saying it, but they're not full rotations because pi is literally like a half rotation. Silly story, and then I'm done. Like, done with silly stories? No, I'm not, but I'm just going to say I am. So pi, I think pizza pie, but it doesn't work because pizza pie, full. So now pi means calzone. 1 pi is 1 calzone. 2 pi is 2 calzones. But see, a calzone, like a little, no, I don't like you anymore. Calzone over 2. There's the calzone. There's pi. There's half of it right there. Which, again, radius of 1. This means 0, 1. 3 pi over 2. Yes. 1 pi over 2, 2 pi over 2, 3 pi over 2. -3 pi over 2. calzone, cut in half, open clockwise. -1, -2, -3. -21 over 2. Even if you just did this. 1, 2, 3, 4, 5, 6, 7, 8, 12, 16, 20. Wait, I try that again. 4, 8, 12, 16. I think of groups of 4. Bring me back. 21 would be 0, -1. 0. 0, 0, right? I couldn't check it. Why? All right. Start here. End here. You're at 1, 0. Next definition. The 6 trigonometric, which I think should be called circular, so I will call them circular. The 6 trig functions. A function's a rule. One input, exactly one output. We already went through that. So we're going to take an input. We're going to take an angle. Someone's going to say, pi over 6. Calzone. I wish I said calzone. Meat lover. Pineapple on ham. No. Is that a sin? Pineapple on pizza? No. We're going to take an angle and we're going to output something following a rule. That's what a function does. Well, there's 6 rules to know. They all take an angle and they all give something different. The sine, whose base word I believe stems from Latin, but it sounds nice every time you say that. It stems from Latin, sinus, which stands for sun. No, seriously, remember I told you the sun and all the quadrants went this way? And so they wanted to study how far we were from the sun. So they said, it rises right here. Oh, rephrase. Let me rephrase. So when it's directly above us, they said, I don't know if that's feet or something. We're just going to call it 1. They decided this is like one measure, one length. When the sun is directly above us at noon, they said that that's 1, which ends up being the y coordinate there. And so now if we go back to here, when the sun is rising in the morning, they say, how far above us is it? Well, when they wake up in the morning, it's eye level. They say it's not above us at all. The height of the sun is 0. And then it's going up till it reaches its maximum of 1. And then it starts setting. And then they assumed overnight while they're sleeping, the sun is 1 below the earth. And then it rises again, where it's back at 0. So I've been told. I don't know. Apparently the base word here stems from sun. The sun has a height. And in general, we can put this over any radius. But you probably know where this is going in just a second. Unit. But that's what the sine function is. You tell me an angle, we tell the y over r. We'll practice it in just a second. Cosine has an abbreviation right there. Take an angle, and you're going to give the x. What that really was, if this is the sun, what it does is basically saying how far, like from the edge of the earth to the center of the kind of positioning of the earth right there is it. It's actually called like displacement. So I'll let it go. But I want to add to this picture this is really the y value. This right here, not the entire length, but this right there is really your x value. So it's a little deceiving. This x means here, and then this y means go up here. And that point would be xy. So in this actually right triangle, if you've heard of right triangle trig, that's where it comes from. We'll do this next class, but just foreshadowing for a minute here. If you remember SOHCAHTOA, this was adjacent, that was hypotenuse. Adjacent, hypotenuse. If you remember SOHCAHTOA, that's opposite, and that's hypotenuse. And if you remember tangent, opposite over adjacent. If not, that's what right triangle trig is, but it actually just stems from this picture anyways. And what did I just say? So means sine opposite over hypotenuse. Cosine, adjacent over hypotenuse. This is the adjacent side. Cosine, hypotenuse. Tangent, opposite over adjacent. Green over purple. So this plays exactly well with right triangle trig that we'll review next class. Sine, cosine, tangent, these are their abbreviations. These are their definitions. That a definition, there's nothing to explore. Someone has to say what it means. Cosecant, secant, cotangent, abbreviated as such. What do we notice about these ratios? We can find them right up here. They're just the reciprocals. We'll just kind of notice that now. I do have it on a future PDF or note slide. So just a reminder, here's sine, y over r. Here's its reciprocal, r over y. Cosine is x over r. Here's its reciprocal, r over x. And tangent is y over x. Its reciprocal is x over y. Those are the 6 trig functions. Definitions, not all that exciting. Okay, so find the value of the 6 trig functions given this following angle. What's the sine of pi over 2? I'm going to take my time with this one, but we did a lot of things. I want to put it together. Pi over 2. You told me earlier 0, 1. So you know how to rotate. So you're thinking 0, 1. We're associating this with the point 0, 1. Sine is y over r. But wait a minute. If we're going to think about a unit circle, which is helpful for the following reason, what's r going to be?
1.
I know we said that a bunch of times tonight. So let's think about the unit circle because it's friggin' helpful, not just for that. What's the y value? 1. 1 over 1, but I don't want to do that ever again. The sine of pi over 2 is 1. What's the cosine of pi over 2? It's x over r. But we're going to say, there's a unit circle, associate the point 0, 1, take the x, 0, put it over the r, 1, 0. What's tangent of pi over 2? We take the y value of 1, we put it over 0, and we say undefined. The reciprocal of sine is cosecant. With all my knowledge of math, and it's not really that much, but a little trick I learned, the reciprocal starts with C. Now I know cosine does too, but I remember SOHCAHTOA. So don't use cosine because that's like the main 3. So I have cosecant, secant, and cotangent. Sine, reciprocal starts with C, cosecant. And this says, just to flip this, or flip my answer, 1. Secant of pi over 2, to take this answer and flip it. Undefined. That's correct. Because this is 0 over 1, and when you flip it, it's going to look like that. So speaking of which, even though this is undefined, when we flip it, this becomes 0. That's kind of cool. Hopefully I've done an okay job, but if all alien and ancestor aside, you need to know your quadrantal angles, pi over 2, pi, 3 pi over 2, 2 pi. Know how to count them negatively. Know these definitions. Even though there's an R there, I'm going to say kind of ignore it because it's 1. And so if you know your points on the unit circle and you know your definitions, this isn't that hard. It's just knowing it. I got to lap this. Man, tonight I planned right on time. Let's do this one more time with negative pi. Start here. Rotate like a calzone. But we already said half rotation is 180. It doesn't matter which way you rotate 180. You're both going to be over here. What's the order pair we want to associate right there? Too slow. Negative 1, 0. Right. Or just too quiet. But you were at least thinking about it. Some of us were just not thinking about it. We're right here. Take the sine of negative pi. Take the y coordinate. Cosine of negative pi is the x coordinate. Tangent of negative pi is the slope. What? I said something I'll tell you later. It's the y over the x. Cosecant of negative pi is the reciprocal. Secant of negative pi is the reciprocal. And cotangent of negative pi, stop, bro. Oh my gosh. Is the reciprocal. What's the domain and range for sine and cosine then?
Negative 1 to 1.
What are we feeding all trig functions? Like, what did we just give them? Or what else did we give it? Those were our outputs, so no, not quite. But we could feed them those things. These are our inputs right here. This is what we give it. This is the input, which is a radian measure. A radian is a way to measure, in general, I'm thinking of another word that starts with like A. Angles. Can we have 0 as an angle? Seems weird, maybe not in high school geometry, but it means rotation. That's another word for like angle. Can we have acute angles? Can we have 90-degree angles? Can we have 180, 270, beyond 360, called coterminal? Can we go back to 0? Can we do negatives? So if we're inputting angles, what was I just trying to suggest? What kind of angles can we think about? 0, positive, and negative, bro. All angles, all real numbers. We can think about any rotation we want. What are the output values? Why? How come? Because of the unit circle. About a half hour ago, I was like, yo, the sun is at its maximum right here. What's the Y value right there? The sun is at its minimum while I'm sleeping. What's the Y value right there? And then at some point in between, it's 0. Actually, a couple points in between when we get to solving trig equations. That's why there's going to be more than one solution to things. But keep jumping too far ahead sometimes. But it's no bigger than 1 and no less than -1. How about cosine? Where's the biggest x value on the unit circle? Right here, 1. Where's the smallest x value? Over there. I feel like I wanted to do something fun, but I didn't know what to do. But I was trying to think of something quick. I don't know. Leave it at that. It has the same range because you're giving back x values for cosine, y values for sine. We can rotate whatever we want. I'll stop there because we're probably brain fried and I have 1 minute left. So a little bit more I told you we wouldn't get through, but you can definitely chunk away. Rational functions, man, if it's been a vacation, good for you, but that is officially due for full credit on Thursday, late credit Sunday night. Radians and part of angles of rotation trig functions officially open, officially due 1 week from tonight, late credit a week plus 5 days from now. So get your rational function stuff done. I'll see you guys on Thursday.
Thank you.